Hello and welcome to part 3 of AQA Chemistry 2018 Paper 1 higher tier. Okay, so we'll just get straight on with the questions. So figure 3 represents different models of the atom. A, B, C, D and E. Which diagram shows the plum pudding model of the atom? That one could be misleading, couldn't it? Because you could think it would be B or E. What the plum pudding row was that the positive was the most central bit, and the negative, as we know, electrons now, were embedded in it because they were the currents, the raisins in the plum pudding. So it's actually B. So tick one box, B. It's a nice, straightforward question, but you could be caught out by that E. Which diagram shows the model of the atom developed from the alpha particle scattering experiment? Okay, so that's actually quite a tricky question, because from Rutherford's work, he didn't know about the neutrons. Okay, so that could catch you out, couldn't it, from A? Because at that moment, he didn't know about the neutrons. So actually that one is C, because he knew there was electrons on the outside and a positive middle, but he didn't know about an internal structure at that point. Okay, so that is C. Okay, next one. Which diagram shows the model of the atom resulting from Bohr's model? Okay, so Bohr, started to figure out the internal structure of the nucleus. So that one is the one we know today, and that's A. Okay. Next question. Define the mass number of the atom. So I knew this was coming up because I talked about it earlier, didn't I? So the mass number is the total, or you could say the sum, the total number of protons and neutrons. Total number. Element X has two isotopes. Their mass numbers are 69 and 71. The percentage abundance of each isotope is 60% of 69, 40% of 71. Estimate the relative atomic mass of element X. So it's taken as an average. Okay, if you have isotopes, for example, like chlorine, okay, that's an average is taken. So would it be under 69? No, because it has to be an average of those two. Between 69 and 70, possibly. Between 70 and 75, not likely because there's more of this one. Okay, or above 70.5, and we know it wouldn't be that one. So it must be most likely to be 69.5 and 70. I mean, you could work that out, but just ask to estimate for that one. Okay, Chadwick, I think it's James Chadwick. James Chadwick's experimental work on the atom led to a better understanding of isotopes. Explain how his work led to this understanding. So Chadwick discovered neutrons. So that gives you 1 mark, just to note that. So Chadwick discovered neutrons. Chadwick discovered neutrons. Okay, so this was important. It was important as isotopes have the same atomic number but different masses. that this is due to isotopes having different numbers of neutrons. Okay. Because I understood why they did it. Because they knew they had different masses, but they actually didn't know why until the neutrons discovered. This wasn't actually that long ago. It was in my my grandparents' lifetime. Neutrons discovered. It's not that long ago. So number 5, the student investigated the temperature change in displacement reactions between metals and copper sulfate solution. Table 2 shows the student's results. The metal and the temperature increase in Celsius. Copper 0, iron 13, magnesium 43, zinc 17. So you can kind of guess what this is going to be about reactivity, can't you? Plot the data from table 2 on figure 4 as a bar chart. Okay, so we've already got plotted for us metal and temperature increase in Celsius. So actually, this is actually fairly easy, but we need to define an axis. So the top number is 43. So what can we go up in? So let's go up in, can we just go up in ones? 10, 20. Yeah, we can just go up in ones. What? Always just choose the easiest axis if you can. Sometimes it's not possible. So 10, 20. So each little tiny square represents 1. 30, so nice and easy for us. 40. And we've put 50 right at the top, but we don't need to go as high. Okay, 50. So it's a bar chart. So with discrete values on the x-axis. So we've got copper, iron, magnesium, zinc. And let's just do one at a time. So copper, 0 for copper. Let's do that. Let's make them all the same. It's not a histogram, so they all need to be the same width. You don't see many histograms in science either. So iron, magnesium, and zinc. Iron, magnesium. You could have given us their symbols to fit in, but we'll just do a full name. Zinc. So copper 0, so it doesn't even have a bar. Iron's 13. So iron. So in the exam, you would have a ruler. I wonder if I can draw. Oh, I'll just draw it so we can. So you can see what I'm doing. Okay, so that bar is going to be like that. So yeah, all draw a straight line in exam. Obviously, I'm just showing you on computer. Iron's 13. Magnesium 43. So that's a lot higher. It was up here. So 41, 2, 3. All the way down. Not doing too badly with that line there. This one's not straight. Okay, but you understand what I'm doing. You can see the method involved. Really high, and then finally zinc 17. They're not as high, but higher than iron. And obviously, I think we can guess what they're going to ask. 15, 16, 17. Done. Okay, so that's done. That would give us our marks. Nice. It's really quite easy, really, isn't it? Okay, so it's actually quite a good question because it's nothing too difficult. The student concluded that the reactions between the metals and copper sulfate solution are endothermic. Okay, I was thinking that's a funny thing to conclude, but it's incorrect. Give one reason why this conclusion is not correct. Because they're giving out heat, so they're exothermic. It said that they increased in temperature, so we just plotted. So give one reason, there was a temperature increase. So it's exothermic. I think they've got their words mixed up there. Okay. Aha, this is what we knew we were going to be asked before that table. The temperature change depends on the reactivity of the metal. The student's results are used to place copper, iron, magnesium, and zinc in order of their reactivity. Describe a method to find the position of an unknown metal in the reactivity series. Your method should give valid results, and we hope so. Okay, so we know the reactivity of these metals. So reactivity series so far. So from experiments, so we had copper at the bottom and magnesium at the top. So I'm just going to write it as a bit of a table here. Magnesium, then it was zinc, then it was iron. So, and that's copper. So most reactive, from the experiment above, least reactive. Okay, so an unknown metal. So first thing we do, we'll try it with copper first of all. So you could add the unknown metal to copper sulfate solution. And observe if a reaction has occurred. So bubbling, color change, all these things will indicate a reaction. Okay. So what we're going to do next? We've got copper. Next one we could do is there's a few different ways of doing this. Bubbling, color change. You could, I'm going to put 2, and then you could do it in also if no reaction occurs. Add to okay. Not much space there. I write it down here. That's okay. You could write it down here. Add to metals, iron, zinc, and magnesium solutions. To see if displacement occurs. You could also, or think another one students may have done in class, I'm just thinking, is measure the increase in temperature, so like we did in the graph. What acid was added? Oh, metals and copper sulfate. Okay, which is increase in temperature. Okay, so we need to provide a little bit more here. Which is increase when metal, so the unknown one, is added to copper sulfate and plot this on graph. So if no reaction occurs, no change, metal is less reactive than copper. If change occurs, place in order of temperature change. That's another way. It's got two methods there. Okay, so draw a fully labelled reaction profile for the reaction between zinc and copper sulfate solution on figure 5. So it's still part of the same question here. Okay, so this was an exothermic reaction, wasn't it? Okay, so exothermic, we've got reactants and products. Okay, so giving out energy, so they actually lost energy. You've got reactants and products. So that's to start off with. So then we've got to add some extra things here. So we've got activation energy, not doing anything. So I'm going to extend that line a little bit, make it look better. So this bit here is the activation energy. That's the activation energy. Okay, so and this bit, not always labelled, but I label it here, is the overall energy change. Okay, so this is right here, exothermic reactions giving out energy. Okay, so the products have less energy stored in them than reaction because it's exothermic. Okay, leave that there for a minute. What's the next question? Okay, this is a little bit different. Okay, so it's not the same as the one. This has got a power supply now. The student investigated the electrolysis of different substances. Figure 6 shows the apparatus. You've got a direct current power supply, graphite electrodes, solid zinc chloride, and a crucible. Okay, so that isn't really going to go anywhere, is it? Yeah, I would guess. Explain why electrolysis would not take place. Okay, as shown, because it's solid. I noticed it straight away. I said, well, nothing's going to happen there. So solid zinc chloride does not conduct electricity. So solid ionic substances, so solid zinc chloride do not conduct electricity. So solid zinc chloride does not conduct electricity. I noticed that straight away. Yes, solid. So yeah, it should too. That's solid. Explain why graphite conducts electricity. Answer in terms of structure and bonding of graphite. So graphite is the carbon sheets. Okay, so each carbon atom forms 3 covalent bonds with its giant covalent. And 1 electron per carbon is delocalized. So these electrons can carry a current with the graphite. Okay. Right, let's go to the next question. The student investigated how the volume of gas produced changes with time in the electrolysis of sodium chloride solution. Okay, so you've got kind of get the other way up this time, isn't it? DC power supply, there's a cork or a bung there, graphite electrodes, sodium chloride solution, and you've got test tubes collecting gas. So you've got hydrogen gas and chlorine gas. Okay. The student made an error in selecting the apparatus for this investigation. How should the apparatus be changed? So with the test tubes, it's not really measuring volume. I know roughly you could do it, but it's not really measuring volume exactly. So that's what you would say. So test tubes do not measure volume. There's no measurement on the side of a test tube. Do not measure volume. So measuring cylinders should be used instead. When you collect gas, you use a measuring cylinder. Okay. Otherwise you can't measure it. Okay. Another student used the correct apparatus. The student measured the volume of gases collected every minute for 20 minutes. Figure 8 shows the student's results. In figure 8, volume of gas collected in centimeters cubed, chlorine, hydrogen, time in minutes. Describe the trends shown in the results. Use values from figure 8. So we need to use the graph for this. Okay. So hydrogen was easy to explain. Let's start with that one. It's a straight line. Okay, so the volume of hydrogen collected is directly proportional to time. So it was produced or collected, I'll say collected. So collected at a constant rate of, let's have a look, so time in minutes, 10. Okay. If it was about 4.5 and 10, so it's about 0.45 centimeters cubed per minute. The chlorine, so chlorine up to, it's not directly proportional, up to 8 minutes is collected at an increasing rate. So yeah, the line was curved, so it's increasing, accelerating up to that point, and then was collected at the same rate as the hydrogen. Okay, so I'm going to stop the video there. Okay, and I'll see you in part 4. Thank you for listening, and I'll see you in part 4.